Hi everyone. Having studied infinite sequences, we're now going to study infinite series. So let's take a look at this definition. So here's our definition for what we mean by an infinite series. So if we're given a sequence of numbers, a sub n, then an infinite series is an expression of this form where we simply sum up all of the terms in the infinite sequence. So remember, the infinite sequence is just going to be the numbers a1, comma, a2, a3, and so on. Now what we do with an infinite series is we take these numbers and we add them all up. And this is what we mean by an infinite series. Now the notation that we use for this is right here. So this is our notation for an infinite series. This is called your summation symbol. That Greek sigma right there, that's your summation symbol. Notice you have down here your indexing variable, the n. So this says that n goes from 1 all the way to infinity. So this is where the n is supposed to stop. Well, in this case it doesn't. It goes all the way to infinity. And then the expression in here, this is your sequence that you're summing all of the terms of. And so this is used to denote this right here. So for example, if we're given this sequence, the sequence 1 over n squared for n from 1 to infinity. So that generates this sequence of numbers, you notice, 1, 1/4, 1/9, 1 over 16, and so on. Then the corresponding infinite series is given by this right here. So you see we have our summation from 1 to infinity of 1 over n squared. And so that's simply going to be the sum of all of our sequence terms. So 1, notice we get this 1 by putting 1 in for this n, right? This is when n is 1. That's how we get the 1. Then when the n is 2, we get 1/4. This is when n is 2. And we add them. And then when n is 3, we of course get 1/9. So that's when n is 3. And then when n is 4, we get 1 over 16. Like that. And so this number, if it exists, is what we declare our infinite series to equal. Now, it is, of course, reasonable to ask, does this even exist or not? All right, does this exist as a number? When we add up these values, do we actually get a finite number? So that's what we need to investigate. Now, in this case, as we'll see, this actually does sum to a finite number. Now, that's unlike something like this down here. Obviously, if we just consider the infinite series from n equaling 1 to infinity of just n, well, that's just going to be 1 plus 2 plus 3 plus 4, ... so on. Well, of course, that is going to equal infinity, right? That's pretty clear that this is not going to exist as a finite number. So that's what we want to do now, is we want to investigate methods for determining if a series converges or diverges, and then if possible, actually evaluate it. Like, can we actually calculate what this number is equal to? That's actually much trickier. It's not too hard to determine if this series will converge or not, but actually determining what it converges to can be very difficult. Now here's a definition that's going to precisely define what we mean by convergence or divergence for a series. And so this is going to define what we mean by the nth partial sum, S sub n, of a series. So if we're given a sequence of numbers, a sub n, then we define the sequence of partial sums, S sub n. So this is another sequence of numbers. to be the sequence in which S sub n is defined to be the sum from 1 to n of a sub I. So in other words, the S sub n, as we see down here, is just the sum from a1 up through an of the sequence that you're given. So for example, right in here you see we have S1 is just going to be a1. S2 is going to be a1 plus a2. S3 is going to be a1 plus a2 plus a3. And so on, and in general then S sub n is going to be a1 plus a2 plus a3 all the way out to an. We then define convergence and divergence for your series like this. We say that the series from 1 to infinity of a sub n converges if the limit as n goes to infinity of these nth partial sums equals a number s which exists. So if this limit, if these numbers as n goes to infinity approach a finite number s, then we say the series involving the an's converges to that number s, and we write that it is equal to s. Otherwise, if this limit does not exist, then we say that the series diverges. So that's how we define convergence and divergence for a series. Now here we have an example illustrating what these partial sums might look like. So let's consider this series, the sum from 1 to infinity of 1 divided by n squared. So this would be the sum of the reciprocals of the positive integers squared. So S1 is going to be the sum of the very first term in the an sequence. Keep in mind the an's here are 1 over n squared. So this is just going to be a1, which is 1. So S1 is 1. S2 is going to be a1 plus a2, so that's going to be 1 plus 1/4, 1 over 2 squared. That's how you get the 1/4. Of course, that's 5/4. S3 is going to be 1 plus 1/4 plus 1/9, which is this, 49 over 36. S4 is 1 plus 1/4 plus 1/9 plus 1/16. 1/16 being 1 over 4 squared, of course. And then so on. And as you see, Sn in general would be 1 plus 1/4 plus 1/9 plus ... all the way up to plus 1 over n squared, whatever you would pick this n to be. And then, as long as this sequence converges to the number s, as long as that exists, we would then state that this series, 1 over n squared, converges to the number s. So that's what we mean by the nth partial sums for this particular series. Now it's not at all obvious, but it is a very famous result that this particular series actually does sum to pi squared over 6. That's a very famous result due to Euler. Now we're not going to prove that result here because it's rather complicated to do, but we will at least be able to eventually prove that this series does indeed converge. So that we will be able to prove eventually. Now if we're given a convergence series, it's oftentimes very difficult to determine the exact limiting value s of that convergence series, in other words, what it's equal to. It's usually very difficult or impossible to do that. However, we do have a lot of tests that we'll be covering where we can use those tests to determine if the series converges or diverges. So we'll know, for example, whether the series is convergent or whether it's divergent, but we may not know exactly what it converges to if it does converge. Well, once we know it converges, we do then have approximation methods that we can use to approximate what s is equal to. So the moral of the story here is it's very difficult oftentimes to determine this limiting value s, but it's actually fairly easy to determine if your series converges or diverges. Now we are going to look at a few types of series here where we can evaluate this limiting value s for convergent series. And the two types we're going to look at are called geometric series, and then we'll look at what's called a collapsing series. Now a geometric series is defined like this. If you let a and r be two fixed constants, then this is how we define a geometric series. So it's equal to a plus a times r to the first power plus a times r squared plus a times r cubed plus dot 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 plus a times r to the nth power, and then it just keeps going like that. So that's what a geometric series is defined to be. And this does occur in many applications. So for example, what is the sum from 0 to infinity of 1/2 to the nth power? Well, that's just going to be 1 plus 1/2 to the first power, see that? Plus 1/4, that's 1/2 squared, plus 1/8, 1/2 cubed, plus 1/16 plus 1 over 32, and so on to infinity. Now we will prove soon that this does actually converge, and we'll be able to exactly evaluate what the limiting value of this series is. In other words, what it's equal to. That's not going to be that difficult to do. Now let's take a look at this theorem that tells us when a series like this does converge and when it does diverge. So let's consider this theorem. If we start out with a fixed constant a that does not equal 0 and r, then if the absolute value of r is between 0 and 1, then this geometric series does converge. And in fact, it converges to a divided by 1 minus r. So we do actually know what this series converges to. On the other hand, if the absolute value of r is bigger than or equal to 1, well, then that series diverges. Now you might be asking here, why do we have the requirement that r in absolute value actually has to be bigger than 0? Why can't we put 0 into this series? So in other words, why can't we evaluate this? You might ask, isn't this always just equal to 0? Because all of these terms would be 0, and shouldn't we get back 0? Well, there's a small technicality here with letting r equal 0, and that is if you're summing from 0 to infinity, then the very first term in this series would be a times 0 to the 0 power, but as we've seen previously, this is an indeterminate form, so it's actually undefined. So that's technically why we can't have r equaling 0. But if instead of starting at 0, you start at, say, 1, well, then it would actually be okay to make this statement. And we actually do have a modified result that we'll see later on for what this series equals if we start at 1 instead of 0. That's a fairly easy result that we'll see later on. Now let's take a look at the proof of this result. This is a very important theorem, so let's go through its proof. So here's how the proof of this theorem works. We first of all consider the nth partial sum, s sub n. So that's going to be the sum from k equaling 0 to n. Notice we had to change our indexing variable from n to k down here because we're going to sum from 0 to n. You see we have the n up here, and so we can't have an n here and an n down here. It wouldn't make any sense. So we actually have to change our indexing variable here to a k. So s sub n is going to be a plus a times r to the first power plus a times r squared plus a times r cubed plus dot 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 all the way out to a times r to the nth power. Now, take note of this. If we take Sn and we multiply by r, so right here we multiplied by r, then multiplying all of this by r right here, what we're going to get is this. Now let's do a little trick here. What we're going to do is subtract r times s sub n from s sub n. So if we take this side right here and simply go minus r times Sn, and we take this, and we subtract from it what we have down here, right here, so we just subtract that, what we end up with is this statement right here, that s sub n minus r times Sn, right? So that's what we have, just by taking the left-hand side here and subtracting this. Now, if we take these terms here, notice that if we subtract the terms down here, you're going to get a lot of cancellation. This is going to cancel with this term. This one will cancel with this one. This one will cancel. All of these up here will cancel, and you'll be left with the first term here and the last term down here. So you see you end up with a statement that Sn minus r times Sn is equal to a minus a times r to the n plus first power. Now what you can do is, from the left-hand side here, let's factor out an Sn, so we can write this as and then divide this over here to this side, and we end up with this statement that the nth partial sum is actually equal to this quantity. So it's equal to a minus a times r to the n plus first power divided by 1 minus r. Remember, this 1 minus r is this one right here. Okay, now what we can do is we can take the limit as n goes to infinity of this quantity. Okay, so now we have this result down here. Let's just scroll down a little further. So we have this. Let's keep that in mind right here. Now notice this. If the r is between 0 and 1 in absolute value, then this term right here is going to approach 0 as n goes to infinity. For example, suppose r is 1/2, say. Certainly 1/2 to the n plus first power goes to 0 as n goes to infinity, right? Because this is equal to 1 over 2 to the n plus first power, so as n goes to infinity, the denominator here is certainly going to infinity very rapidly. 1 divided by infinity is 0. So this term will go to 0 as long as r is between 0 and 1. So we have this result then. If the r is between 0 and 1, then the limit of the Sn partial sums is going to be a divided by 1 minus r, because this term is going to 0, and we end up with this result right here. So that is what the geometric series sums to. On the other hand, if r is bigger than 1 in absolute value, well, in that case, then these terms here actually go to infinity, right? For example, if the r is 2, say, well, certainly 2 to the n plus 1 is going to be going to infinity as n goes to infinity. Certainly. So you see a times r to the n plus first power will be going to infinity if the r is bigger than 1 in absolute value. And so in this case, we see that the geometric series diverges. And so there you go. So that's our proof. Let's take a look at a few examples. So let's evaluate this infinite series, the series from 0 to infinity of 3/4 to the nth power. Well, in this case, we see that the r is equal to 3/4, and also note the a is 1 in this case. And so r does satisfy this. And so therefore, we see that the sum from 0 to infinity, 3/4 to the n, is going to be right here. 1 divided by, this is the a, right? A divided by 1 minus r. And so that's 1 over 1/4, which is 4. And so there you go. If we were to add up all these numbers right here, you'd see that you would get 4. And you can try that out. Add up these numbers out to 10 or so terms, and you'll see that you get a number very close to 4. Now let's take note of these two important results that we have from this theorem. So this is just a restatement of the theorem part A right here, that the sum from 0 to infinity of r to the n is 1 over 1 minus r. Now this is in the case when the a is 1, okay? And let's also notice this. If we sum from 1 to infinity, this series, this modification of the geometric series from part A, you notice we just leave off the first term here, is going to be r divided by 1 minus r. And the reason that is, as we have pointed out down here, if you look at the sum from 1 to infinity of r to the nth power, that's going to be the sum from 0 to infinity of r to the nth. Take away the very first term in this series, right? So minus 1, and you end up with this statement right here. And simplifying this, very simply, you get r divided by 1 minus r. So that's how we end up with this result. So these are two very important results that you should note. The sum from 0 to infinity of r to the n is 1 over 1 minus r, as long as r satisfies this. And the sum from 1 to infinity of r to the nth power is r divided by 1 minus r. Now that is for r satisfying this. Now in this case down here, you notice we can actually put 0 in for r, because down here we start with 0 to the 1 power, which is okay. That's just 0. Whereas up here we start with 0 to the 0 power, and that's not acceptable because 0 to the 0 is an indeterminate form. Let's take a look at a few examples here. So for example, what would be this geometric series? Now you see we're summing from 1 to infinity of 3/4 to the n. Well, following the formula that we just derived, since we're summing from 1 to infinity and 3/4 is less than 1 in absolute value, we see that this is going to equal r, which is 3/4, divided by 1 minus r. And so that simplifies as 3/4 divided by 1/4, which of course is 3. And well, that makes sense because if you recall, we saw that the sum from 0 to infinity of 3/4 to the n was 4. And so if we take away the first term in this series, we get this series. And taking away the first term from 4, well, you end up with 3. Okay, so that makes sense. Now let's take a look at some properties of infinite series. Now here we have some common properties that we use to manipulate infinite series. So this theorem makes the following statement. If we're given two convergent series, so suppose that the series involving the ANs converge to A, and the series involving the bn's converge to capital B. And also let's let C be any fixed constant. Then we have these three properties. So you notice the first property makes this statement. If we look at the summation of C times A sub n, you can just move this C out in front of the summation. That's what this statement is saying. So this will equal C times the summation of the ANs. And since this is equal to capital A, you get C times A. So in other words, for any fixed constant, you can move it in front of the summation. We also have this result that the summation of AN plus BN is equal to the summation of the AN plus the summation of the BN. In other words, you can distribute the summation symbol into the AN and the BN separately, and you just get A plus B. And the same thing for minus. You can also distribute the summation. Now these results shouldn't seem surprising, and you also notice that they mimic results that we have seen previously, like for limits. For example, the limit as x approaches c of f of x plus or minus g of x is the limit of the f plus or minus the limit of the g. So it mimics these results that we've seen previously, and in fact, using these results for limits is how you actually prove that these results hold. Now let's take a look at some examples. Let's consider this first example right here. So suppose we want to evaluate the summation from 0 to infinity of 2 to the nth power minus 5 divided by 6 to the nth power. Now, what we're going to do here is manipulate this so that we get two geometric series appearing. So we're going to write it like this. So down here, take note what we're going to do. So first of all, we're going to take this fraction and break it apart like this. So you see we're just using the property that A minus B over C equals A over C minus B over C. So we're just using that result. Then we can use property C and split this summation up like this. So you notice that we distributed the summation to the first term and then the second term, and we have minus in there. And also at the same time, notice that we pull the 5 out in front of this summation. That's using part A from this theorem. And we also wrote 2 to the n over 6 to the n as 1/3 to the n. So now you clearly see that we have two geometric series. So the first one right here, that will equal 1 over 1 minus 1/3, as we have right here. And then this one, 5 times this one right here, will be 1 over 1 minus 1/6. And so you see this is going to be 1 over 2/3, so that's going to be 3/2, just like we have right here, minus 5 times 1 over 5/6, so that's going to be 5 times 6/5. That's exactly what we have right here. And then all of this simplifies to negative 9/2. And there's our answer. So there you go. What we did with this, once again to summarize, is we simply broke this term up, and then using theorem 9.2.10, we simply distributed the summation to both terms, moved the constant outside, and then we had two geometric series that we could evaluate. Now here we're going to take a look at another type of infinite series for which we can actually evaluate what it sums to. So this type of series is a very special type of series, and you don't run across it very often, but it's called a collapsing or telescoping series. So let's take a look at this example. So here we want to evaluate the summation from 1 to infinity of 1 over n squared plus n. So let's note that we can take the an terms, the 1 over n squared plus n, and using partial fraction decomposition, note that n squared plus n is equal to, of course, n times n plus 1. So we can write this, what I have circled here, as a over n plus b over n plus 1 using partial fraction decomposition. And then let's see what happens when we sum up this series. So using partial fraction decomposition, we consider this right here. Okay. And now we have to solve for the a's and b's. So remember what we do there is we recombine this side, so we add this side together and solve for the a's and b's. So just very quickly here, you'll find that the a is 1 and the b is -1. If you don't recall how to do that, notice if we take the right hand side here and simplify it, we'll get a times n plus 1 plus b times n over n times n plus 1, just cross multiplying or by finding a common denominator, and of course that is supposed to equal 1 over n times n plus 1. So setting the numerators now equal to each other, setting this equal to 1, and then picking values for n, like for example -1. If we put -1 in for n, this goes away. We get negative b equals 1, so b is -1. And if we put 0 in for n, we get a times 1 equals 1, and so that's how we get these results. Okay, so what we have now is that this original series up here so this series is equal to, that's the one we started with, the summation of 1 over n minus 1 over n plus 1. And so that's just using partial fraction decomposition, so we didn't change anything. It's simply the fact that this is equal to 1 over n minus 1 over n plus 1. Now let's see what happens when we write out a few of these terms, what this summation is equal to, expanded out. So what we get is this down here. So you notice this is when n is 1. So if we put 1 in here for n, we get 1 minus 1/2. So right there. Plus, and then this is what we get when n is 2. So we get 1/2 minus 1/3, right? If I put 2 in for that n. Now we'll see why I have those crossed out in a second. Now when n is 3, you get this. And then when n is 4, you get this. Put that right here. All right, now you can see how the cancellation works and why we call it a collapsing series. You see, we have this -1/2 cancels with the +1/2 here, so that's why they're canceled out. -1/3 here cancels with this 1/3. -1/4 cancels with this 1/4, and so on. So everything collapses in on itself and cancels. And the only thing that we're left with is 1 at the front. And so we see that this summation is actually equal to 1. And so we see that's how a collapsing series works. That's pretty tricky. Now there is one small technicality here that we really should pay attention to. And let's scroll down a little further and see what that technicality is. Now we really should, to be proper about this, Recall that, we had the 1 left at the front of this series and everything else canceled with each other, so we concluded that the series summed to whatever was left at the front. However, we really should prove that the nth partial sum converges to 1. That really would be the proper way to do it. Now, let's notice that the nth partial sum here, well, that's the sum from 1 to n of 1 over k minus 1 over k plus 1, right? So all we did here is just exchange the infinity with an n. And if we write out the nth partial sum here, you see we get 1 minus 1/2 plus 1/2 minus 1/3. Next term would be plus 1/3 minus 1/4, and so on. And then the last term is when k is n, and that's going to be 1 over n minus 1 over n plus 1. And by the way, this 1/3 here cancels with there would be a 1/3 right there. The next term would have a 1/3 in it. This 1 over n here cancels with the previous term. There would be a 1 over n right here, negative 1 over n in the prior term. And so you see the nth partial sum is actually equal to 1 minus 1 over n plus 1. Now you can see if you take the limit as n goes to infinity of your nth partial sums, that's what we have written right here. Well, obviously this term right here goes to 0 as n goes to infinity, and you're left with 1, which is what we had previously concluded. But this is the proper way to do this type of problem. However, for most of the problems we encounter, it's okay if you do it like we have up here. Now in this example, we want to evaluate the summation from 1 to infinity of negative 1 to the n plus 1 power. Well, if we write out a few terms of this series, so when n is 1, if we put 1 in here for that n, we get negative 1 squared, so that's 1. Then if we put 2 in for the n right here, we get negative 1 cubed, so that's minus 1. Then if we put 3 in here for n, we get positive 1 again. So you see we get this alternating summation, 1 minus 1 plus 1 minus 1 plus 1 minus 1, and so on. Okay. Now you might erroneously think that this is a collapsing series. You might look at this and say, well, I see this negative cancels with that one, this one cancels with this one, and this one would cancel with the next one, so shouldn't my series equal 1? Well, no, it shouldn't, because as we'll see, the nth partial sums do not actually converge to anything. Another way to see this is that you could have also done your cancellation like this. Suppose that we canceled this 1 with this negative 1 right here, and left this negative alone, and then this 1 here we could cancel with this 1. This 1 we could cancel with another 1 over here, so now we've left the negative 1 out front here. So is this sum 1 or is it negative 1? Which one should it be? You see, depending on how we chose our cancellation, we could get either one. Well, obviously this summation is not going to exist. It's going to diverge. And that's because if you look at the nth partial sums, they do not converge. So let's take a look at the nth partial sums. So if we look at S1, you see we get 1. If you look at S2, that's going to be 1 minus 1, that's 0. If you consider S3, that's going to be 1 minus 1 plus 1, so that's 1 again. S4 is going to be 0. And S5 is 1. S6 is 0. So now you can see that you have this alternating pattern. 1, 0, 1, 0, 1, 0, 1, 0, and so on. So therefore you see that the limit as n goes to infinity of your nth partial sums does not exist, and so your series diverges. And so that illustrates why in the previous example, even though we saw the collapsing occurring, we still looked at the nth partial sums to verify that they really did converge. Now this is an example that you don't normally run across, but this illustrates why you really should consider the nth partial sums and not just trust that your series sums to whatever's left over at the beginning. But normally this won't happen. Normally, for the problems we're going to be considering, it is okay if you do cancellation and just look at what's left over at the beginning. Let's take a look at one more example. Now here we want to evaluate the sum from 1 to infinity of 1 over n squared plus 3 times n. So let's notice that the denominator here factors as n times n plus 3. So now using partial fraction decomposition, let's write this, which is 1 over n times n plus 3, right here, as a over n plus b over n plus 3. And of course, recombining this side right here, we get this. And then setting a times n plus 3 plus b times n equal to 1, picking strategic values for the n like we did previously with partial fraction decomposition, you will find that the a is 1/3 and the b is -1/3. So therefore we have this result. The summation from 1 to infinity of 1 over n squared plus 3 times n is equal to the summation, and notice we pulled the 1/3 out here. It's going to be the summation of 1 over n minus 1 over n plus 3. Notice right here, we've actually pulled the 1/3 away from both of those terms. So right there it is. Okay, now let's see if this collapses. So let's write out a few terms of this series. So if we write out a few terms, we're going to get 1/3, right there's our 1/3. And then in these big brackets here is our summation. And let's see how the collapsing occurs. So the first term here is when n is 1. Notice if we put 1 in here for n, we get 1 minus 1/4. Right, so there we go. This is when n is 1. Right here, if we put 2 in for n, we get 1/2 minus 1/5. That's when n is 2. Right here is when n is 3. Then n is 4. And 5. Now let's see if we can identify collapsing. Well, we see the -1/4 here cancels with this 1/4 all the way out here. So those two cancel. The -1/5 here cancels with this 1/5 all the way out here. So that's why they cancel. Now the 1/2, there aren't any other 1/2 terms out here that are going to be occurring. You see, because this is, 1/4, and then it goes to 1/5, and 1/6 would be the next term, and you have a minus 1/7, minus 1/8, minus 1/9, so you're not going to get any more -1/2s in here. So this doesn't cancel with anything. Similarly, the 1/3 doesn't cancel with anything, because you see you go -1/6, -1/7, -1/8, you're not going to get any more -1/3s. So that 1/3 doesn't cancel with anything. But from here on out, this 1/4 right here, that canceled with this 1/4 all the way back here. And then the 1/5 canceled with this one. Now the next term would have a 1/6 that would cancel with this one here, so this one cancels with one that's occurring over here in the dots, and so on. So you see what we have left over is the 1, the 1/2, and the 1/3. And that's what this series is going to sum to. So our answer is going to be 1/3 times 1 plus 1/2 plus 1/3 which is what we have right here. And simplifying that, you get 11 over 18, and there's your answer. So this is equal to 11 over 18. And there you go. So for this problem, in comparison to a previous collapsing series problem that we looked at, you notice we had to go out a few terms until we saw that everything was collapsing. And then whatever was left over at the beginning is what our series is going to sum to. And let me mention one other thing. You notice that we didn't bother to look at the nth partial sums and verify that they converge to 11 over 18. Well, that's because if you look at these terms here, you see the 1/4, 1/7, 1/5, 1/8, and so on. The nth partial sum would contain some of the terms at the end, but they would all be of the form like 1 over n, 1 over n plus 1, 1 over n plus 2 perhaps, but you can see they would all go to 0 as n goes to infinity anyway. So that's why we didn't really consider the nth partial sum for this example, because we could see that these terms are all going to 0. Now with the prior example we looked at with the summation of -1 to the n plus 1, if you look back at that, you'll see that these terms at the end were not going to 0, so that's why your nth partial sum diverged in this case.